Hey folks, time for lesson number 2, friction. So, this lesson is going to be slightly different than the last one. The basic thing, the big change is going to be that the normal force is not going to be the force of gravity when you find the force of friction. So, you're used to using mu mg, don't, okay? Because it will not be mu mg anymore most of the time in this class. You're going to have to start off by finding the normal force before. So, a bit of a review of friction. So, initially, Aristotle thought that objects would stop if there were no forces acting on them, that they needed some sort of impetus to keep them moving. But what he didn't realize was that there are always forces between any two objects in contact that are slowing them down. There's an attraction due to gravity, due to the surface between any two objects in contact that are basically slowing them down. And the force is actually the normal force. So it's not the force of gravity really that's causing it, it's the normal force. It's the Newton's third pushing back force that opposes gravity that creates friction. So for something on a surface of a net force of 0 and be at rest, you need the force to be 0. So here's the trick. Your vertical forces are always going to equal 0 for friction questions. So you're going to start off a net force with the vertical part first, with the net force being equal to 0, and then all the vertical forces listed. And then you can use that to figure out what the normal force is. So, as we've seen, if you're on a slant, the normal force and the force of gravity, because they're vectors, are not going to be the same, okay? So if there's any other vertical force on it other than the force of gravity, your normal force is not going to be the same, especially if your normal force is not exactly equal to the force of gravity in both direction and magnitude, meaning you're on a flat surface with no other vertical forces. Fg is not equal to Fn. You can't use mg to find your normal force, okay? So forget that from grade 11. So friction is the attractive force between two objects that opposes motion, and it's always opposite to the direction. So once you get to friction, friction's direction will always be backwards. It's a little confusing because the normal force does have a direction that's up, but when you multiply it by the coefficient, which is dimensionless, it becomes backwards. It's really because the normal force in this case is more of a magnitude. It's not actually pushing the object up when we're sliding it forward or backwards. So the direction for friction is always going to be opposite the motion. So to find it, we use the equation mu Fn. So the coefficient times the normal force. Now the trick is going to be, it's going to be whatever the component of Fg, usually if it's on a slant, is that's perpendicular. So if you'll notice, the y component of Fg here is actually the same as Fn. So Fn in this case is going to be the y component of Fg, not mg. This will be a little different if you're pulling or pushing something. When you pull, if you're pulling, you're actually going to create a little force up that you're going to have to add. If you're pushing something, you're probably going to have a little vertical component down you're going to have to add to vertical. If I'm really mean, I'm going to give you a question where you don't know how much you're pushing or pulling, and you're going to have to use two equations with two unknowns. But that's as crazy as it gets. The ones on a slope are usually the easiest ones. So the coefficient is dimensionless. It's the ratio of the force of friction between the two objects. It has to be determined experimentally, okay? So I'm either going to give you enough information to solve it, or you're just going to look it up. Just if there's ever a missing one in a question, just Google it. You can find all the coefficients for just about everything. It's given the symbol mu. You can do mu, or you can, if you just write a u when you're writing it, if you're trying to hand things in electronically, that's fine. I'll know what you mean. Just put a small u. And it's dependent on the two materials. So for example, why driving on black ice sucks is that rubber on dry asphalt has a coefficient of friction of 1, which is about as big as it can get. Rubber on ice has a coefficient of 0.005. So basically, 1,000 times less, meaning that there's 1,000 times less force slowing you down on your car. So there are also two types of friction. Honestly, don't overthink this. Static just basically means the force necessary to get something moving. Kinetic friction is the force when something is already moving. the way you'll tell is I'm either going to give you a static or a kinetic coefficient. Just use that one. That's really the only difference in the math. So, typical question. Let's say you have a wet road exerting force on the tires of a car going up a hill. And what's the net force pushing the car up the hill? Now, this one is kind of weird because with a car, the friction on the wheels is actually what's helping you. Friction isn't backwards. Friction is actually the force that's driving you forwards. So, how do we do it? Well, the first step in all of these is find Fn from the vertical net force. Now, the vertical net force will always be 0 for these questions, okay? I'm not going to give you any where they're sinking to the ground or rising up off the ground. That's just ridiculous. So, the net force will in the vertical direction. We're just going to look at vertical arrows right now. So you'll notice I've already aligned this basically so that from the point of view of the car, I've bent the whole world by 10 degrees. So 0 is the normal force plus your y component of your force of gravity. So the normal force must be minus the y component. So basically the exact same force, opposite direction to cancel it out. The y component is Fg cos theta because it's adjacent in the down direction. So negative, the opposite of that would be mg cos theta because mg is what your F force of gravity is. That's still the same. Cos 10 degrees up. So the normal force is 14,500 newtons up. Then all you have to do, use that to find the force of friction. So Fn is, oopsies, the same. The force of friction is mu Fn. There should be a mu there, sorry. 0.55 times your normal force, so 8,000 newtons backwards. Remember, it's always going to be backwards because it's force of friction. Then you just use that to find your net force, where 8,000 newtons. So look at your x arrows. Well, there's 2. There's the x part of the force of gravity is pulling me backwards. There's the force of friction that's pushing me forwards. So those are my net forces. One is forward, one is back, because friction's always back. Sorry, not friction, my bad. In this case, friction is the forward force because it's pushing you forward. The hill is trying to pull you backwards. So, as I said, the trick with this is trying to keep track of which direction your arrows are in. So once you've picked a direction for forward, make that your forward direction. So 8,000 newtons forward minus 2,600 newtons forward, make this backwards. So your car is going up at 5,400 newtons forward. So the reason I gave you this example is this is the only case where you will ever plug a friction in as being a forward direction. It's with a car driving up something on wheels, driving up a hill. Okay? Everything else, friction is always going to be backwards. By the way, if you were to solve this and got a net force backwards, that would actually mean there wasn't enough friction to get the car up the hill. The car will be sliding down. So if we did this again maybe on ice, you might not actually be able to get up this hill, and that would actually mean that it was physically impossible for you to get up the hill. The last question I want to give you is a more typical question. It's, let's say you're pushing a box down a ramp and you need a certain amount of force to get the box moving. So we're dealing with static friction, and you're trying to find the coefficient. So for this one, remember the whole trick, you've got to do free body diagrams for these. I know people hate them, but they got to be done. Otherwise, you have no idea what's in what direction. And in this case, it's really important because you'll notice the applied force, if we're pushing it down the ramp, the applied force is actually going to be in the same direction as the x part of gravity, because you're going down the ramp. So this gravity is going to help you. The force of friction will be the one in the backwards direction. So we'll make all these forward, all these backwards. Start off, find the normal force. Again, there's only 2 forces in the vertical direction. They've got to equal 0. So the normal force must be the y component. So mg cos 15 is my angle. So 520 newtons up. Then, to get it moving, the net force horizontally must be at least 0. Anything more than 0 is going to give you an acceleration down. So with static friction, you basically are solving for 0, for a net force of 0, because anything in addition to that will actually give it an acceleration. So look at your x. I've got my applied force, I've got my x component, and I've got my force of gravity. So, well, I know the applied force, 65 newtons. The x component is mg because it's opposite sine 15. Those are both forward. You can see from the diagram. Backwards is my force of friction, which is just mu Fn. Well, so it's 65 newtons forward plus 170 newtons forward. I'm going to make forward my positive direction. So I'm going to change that backwards to a forwards. So it'll be minus 520 because that's what my Fn is, times mu. Bring the mu over, make it positive, add these two up. Then you divide, and you get 0.45. Notice the units and directions are going to cancel. This is going to be true if you did it right when you solve for the coefficient, because coefficients, remember, are dimensionless. They don't have a direction. They don't have a magnitude. So these are the two most common questions. You're also going to get ones that are basically pulling a ramp, pulling something at an angle. With those, again, the difference will be there might be a third thing in your Fn. All right, that's the end of today's lesson. Hope you do well on this worksheet.